Good morning. This is the Level 2 Allegro CL Lisp programming class, and we're going to deal with some higher level topics that were dealt with in the elementary class. There is a great deal of material, so we're just going to start right in. Just a quick thing for people using WebEx, if you've not used it before, we're all connected by phone, so that if you want to say anything, just break right in with a question, and I'll answer it. It might be useful, though, for the people other than me to click on the mute button while you're not talking, because that would mean any extraneous noise won't come in for the recording. You can also type into the chat box on the lower right-hand side, and I'll notice it after a second and respond to it. And you can also click on the raise hand button, and that will indicate something next to your name, which I will notice after a bit. And so we're going to be looking at slides and also going to the I have a running Lisp, and from time to time we're going to go look at that and try out some of what we're talking about there. So the goals for this course, we assume that you know how to write functions. We didn't, in the Level 1 course, talk about the debugger much, but presumably you've run into it at least once, and that you understand the basic data concepts of Lisp and Lisp processing. And here we're going to do more discussion of functions, discuss macros in some detail, and discuss object-oriented programming. The object-oriented programming system in Lisp is called CLOS, and we're going to get a fairly broad introduction to that. The course is 3 two-hour presentations. The lecture, question and answers, just ask questions at any time. And we have sample code, which will be running during the course. Good morning. We just started. This is the second slide, so you haven't missed much. We're recording the session today, so
okay, thank you very much.
And so there are lecture notes available at www.franz.com/lab. You have to put in the /lab because there's no link from the main page to it. And there's also homework there. We recommend that you try the homework. We'll go over the homework in the beginning of the second session and the third session, and one-on-one help via email. And we'll give the email address shortly. Today we're going to cover advanced features of Lisp functions, some additional data types, structures, hash tables, and some discussion of manipulating bits and bytes. Then we're going to go into some detail on the subject of macros and defining macros, and the question as to whether sample code will be available. On that website, you have a copy of all the slides, and you also have a copy of the homework and the homework answers. And if you bring up the slides, if you have let's see, I think it's in an HTML format or a PDF format, and if you take it in HTML, you can just get the code by doing cutting and pasting. So everything you see on these slides is available to you. Let's see, we're going to go into some detail on defining macros and say what macros are, and we're also going to discuss a thing in Lisp called closures, which are a special kind of operator. Now, there are quite a lot of slides today, so it's quite likely, actually, we won't run through the end of today's slides, and if that's true, we'll just pick them up tomorrow at the beginning of the class. We'll finish up any slides. For a variety of historic reasons, the slides are slightly unbalanced between the 3 days, and we've never reorganized them. So we just by the end of the course, we'll have got through all the slides for all 3 days. In session 2, we're going to talk about CLOS, basically the whole session. In session 3, we're going to talk about a number of other topics, performance considerations with CLOS, garbage collector, error conditions, and then something which is specific to Allegro CL, which is using the integrated development environment to write programs on Windows. There are homework sessions available at the www.franz.com/lab website, and we strongly recommend that you try and do the homework. Will be a little bit of reviewing of the homework exercises at the beginning of the next and the third class. The email address for questions of any kind, either technical questions or general questions about Lisp or whatever you like, is training@franz.com. My personal email address is dm@franz.com, but the advantage of training is it's seen and recorded, while a message that's sent just to me, if I'm not here to read it, it won't get seen until I do get around to reading it. And I'm not, I have, because, I get lots of mail, lots of junk mail, unfortunately, like we all do. There's not 100% guarantee that I'll see something sent personally to me. Now, we're going to be running Allegro CL. Well, it says 7.0, and that's what we recommend that you use. There's a trial version available at www.franz.com. But if you have Allegro CL 6.2, that's fine too. Really, up until the third day, there are no differences in the material we're studying between 6.2 and 7.0, and the differences on the third day when we're talking about the IDE are, from the point of view of what we're doing, fairly minor. And in fact, today I'm using a version of 6.2 because that happens to be what's installed on the computer I'm using. So if you haven't downloaded the trial version or you haven't got a licensed version, certainly do that as quickly as possible. As I say, the trial version is free. We'll be basing this on Allegro CL on Windows, and when we go to the list to look at examples, we'll be seeing a Windows version. But if you're using a Unix version, everything we're discussing up to the discussion of the IDE on the third day works perfectly well on Unix. It's just on Unix you normally use Emacs as an editor, and here we'll be using the IDE editor, but the differences aren't great from that point of view. Good morning. We just started. I'm just going into the introduction to the class and the material that I've covered. Most of it will become clear later. We are recording the session today. That's why you see some WebEx people. So I think all the regular students are here, and let's go ahead. So let's start out, and we're just going to talk about functions in somewhat more detail. In the elementary course, and what you might be used to, the way to define functions is to use the macro defun. But there are three other ways to define functions. There is the Lambda construct, which defines what's called an anonymous function, that is, a function without a name. There is the flet and labels, and those are macros or special operators which define local functions, which are used in the body of the flet or labels form and then forgotten about, in the same way that when you use let or let star, you define local variables which are used in the body of the let form and then forgotten about. So flet and labels are like let and let star for defining functions rather than local variables. So here, once again, it should be used to this, is the standard defun method of defining a function. Its components are the word defun, which tells the system what you're doing, a symbol, typically a symbol naming a function, an argument list, called arglist here, and in this example, the argument list contains one element, the argument x, then you can have a string, which is interpreted as a documentation string. And you can also have a number of declarations which tell the compiler, if you compiled this function, that the information about the function itself, its arguments, and also local variables within the function. Here we are telling the compiler that the argument is going to be a fixed num. And I say tell the compiler because essentially the interpreter, if you ran this function uncompiled, the interpreter simply ignores declarations. They have no effect on it. The declarations are to tell the compiler, give it information which will allow the compiler to produce a more efficient compiled version of the function. And in particular, in this case, if you tell the compiler that the argument is going to be a fixed num, then it's not going to do a check to see whether it's a valid argument to plus, and it's not going to do assuming it's a number, it's not going to add code to determine whether it's a floating point number or a big number or ratio or a complex number or any of the other kinds of numbers which would be valid arguments to plus. Instead, it's going to write code that is going to apply the function plus to fixed nums only. And the problem with this is if you then later call the function double with a value which is not a fixed num, you will get an inaccurate result. And possibly you will not get an error because it will just simply look at its argument, assume it's a fixed num, and act appropriately. The important thing to remember about declarations, we're not going to go into them in great detail, but the important thing to remember about them is that they are a promise that you are making to the system. The system isn't going to check that you're keeping your promise. It assumes that you are. The whole point of the declaration is to get rid of code that would determine the nature of X because you've told it it's going to be a fixed num. So there's no checking. Once you've compiled this in a way that declarations are trusted, there are no checking to see that you actually gave it a fixed num because it's your promise and it's your code. And then finally, I got through the declaration form, finally the actual body of the function which does the work. And all it does in this case is add the argument to itself. The argument list contains names for variables, and they get their values from the arguments provided when you call the function. The arguments persist throughout the body of the function. That is, you can refer to them anytime in the function, and they are not typed by the definition. They are typed by declaration, an optional declaration. You can add a type, but the actual position or information in the argument list or the body of the function doesn't type the arguments at all. So any list value is always valid to be passed as an argument. Now, if it's not a proper argument to the function, if you don't give a number here, plus only is valid for numbers, then you're going to run into trouble. But there's nothing invalid about any list type being passed as an argument. And then argument lists may contain optional and keyword arguments, as we're about to describe. Now, both optional and keyword arguments are ways that you can define a function and allow it to take additional arguments which you either supply or don't supply as the situation is called for. Every function definition has 0 or more. It doesn't have to have any. In this case, there's one required argument. Those have to be supplied in any call to the function. And then there are various additional arguments which can be supplied or not. There are essentially two kinds of optional arguments. One of them is called keyword arguments, and the other is optional arguments, and we're doing them keyword arguments first. So in this argument list, there are two keyword arguments defined, stream and use graphics, and the format here, we're going to go into this more detail. The stream keyword argument is given a default value as the value of the global variable standard output, and use graphics is not given any default value at all, so it gets the default value nil. Now here's the body of the function. We calculate the size of the array, and then we output this size to the stream. The stream either to standard output or whatever value is specified. And we use the useGraphics argument to determine whether we should call a function called drawSize in some kind of graphical fashion, or whether we should just print it using the standard Common Lisp print function. Now, you can't grab this function and run it because we haven't defined a function drawSize. That's not a standard Common Lisp function. You would have to define one in order to get this function to work. This is just an example. Print obviously works, and you could either define one or you could, put some other predefined function in there if you wanted to test this. Calls to function look like this. Open parenthesis, the function name, and then the argument. Here we have, we're assuming the value of the global variable myArray is an array. We're calling it just with the one required argument. In this case, we call it with the one required argument and the keyword argument stream with its value, some open file. So you call the function with any number of keyword arguments. You can put them in any order, and you can call it with 0 or all of them. The reason you can put them in any order is they're always in the form, the keyword name, and then its value. Now, notice when we define the function, the arguments here, they aren't keywords. These are just ordinary symbols. There's no colon defined there. But they take the name of that symbol, and then they create a keyword with that name using the same print name. A keyword is a special kind of symbol, which always evaluates to itself. And therefore, the label of the argument is then given here, :stream, and then the value. Because you're giving a label to the argument, that's why you can specify them in any order. And you either specify them or not. There is no ambiguity if you leave keyword arguments out or if you include them in whatever order you put them in. If you're interested in efficiency, and you would be for a function which is called a very large number of times in a very large loop, then it does cost a little bit more to have keyword functions because the argument list must be parsed. And you typically use these for arguments that are only rarely needed. If you always have to specify a value for a keyword argument, then make it a required argument. There's no reason for having a keyword argument. And also, it's useful when you always have to specify a value when you're doing one particular thing and always have to use a different argument when you're doing another. So different calls will use different groups of arguments. Another case for keyword arguments. So again, we have this and key says what follows. The argument is either a symbol itself or a 2-element list or a 3-element list. The 3-element list gives you the third element is an additional symbol, which will be T or nil, depending on whether the argument was explicitly supplied. Because all of these arguments get a default, either the default that's supplied here, standard output, or the default nil when nothing is specified, useGraphics gets the default nil, there's not necessarily any reason that you can distinguish between the value being supplied and being the same as the default and the value not being supplied. And every once in a while, in programming, you want to know whether the function was called with an explicit value supplied or whether it was just depending on the default. And if you want to know that, you can use the 3-element list. And the default's nil if no other default is supplied. So now the other kind of optional arguments are just called optional arguments. they are defined in an argument list with the Lambda list keyword and optional rather than and key. Their format is much the same, an argument name, and either in a list with a default value and also supports the 3-element list with a supplied T. You can put a symbol there, which will be T or nil, as the argument is or is not specified in the call. So here we have 2 optional arguments. And again, you call it either with, here's the one required argument. Here we have the one required argument with the value for the stream argument. Now, the thing is, you can call the function with any number of optional arguments, but what arguments you are passing is determined by position. Therefore, if you want to specify the second optional argument, use graphics, you must specify a value for the first one as well. This is somewhat annoying. I wonder if everyone could press the mute button, because we're getting a little feedback from some of the phones. And then if you want to ask a question, which you can do at any time, just unpress the mute button. That would be good. So by position, you can specify the second optional argument. You must specify the first. This is actually annoying sometimes. This is one reason why keyword arguments are advantageous. Again, optional arguments cost a couple of microseconds. Not a big deal if the function's only called a few times. It is a big deal if it's in a huge loop. Because, again, Lisp must parse the argument list. And use, so optional arguments should be used when arguments are only rarely needed and there aren't very many of them. You never really should have more than 2 or maybe 3 optional arguments. More than 3 optional arguments, and it becomes just very annoying to use them, because you keep, say you've got 5 and you want to specify the 5th one, you have to remember what the defaults are for 1 through 4. And you know, you then have to go look at the manual, or maybe you can't find it out. Keyword arguments, we have 5 optional arguments. You make them keyword arguments. You can specify any one you want without having to worry about the rest. Just an example here. Here's an optional argument where we're not giving it a default value. And then we come down here and we say, well, unless it's a number, we're going to set it to 1. In other words, if it were its default, which is nil, or if it was specified to be some value that wasn't a number, we're just going to ignore that and set it to 1. And then we call it and add the first required argument to the optional argument, and the optional argument having the value 1. In the second case, we're giving it the optional value 1, and we're also doing a symbol here that indicates that the optional argument was called. We're still getting feedback from somebody's line. Could everybody press the mute button under the participants thing? Maybe we'll get the feedback to stop, because it's just kind of a background noise.
Okay. David, I'm sorry, but I don't have a mute button on my phone. And
no, not on your phone. On the WebEx, I think.
Okay. The one that's grayed out. So the one.
Oh, it's grayed out. Okay. All right. So we'll just live with it. No problem. So in the second case, we give it a default value 1 rather than doing a test and setting it, and we also do something that says whether it was supplied or not. And here, if it was supplied and it's not a number, we print out no non-numeric increment. Otherwise, we just call n. Now, if it wasn't supplied, we know it's a number because we know its default value is 1. So in this first case, if we had given it a non-number, we would have, it would just ignore it and set it to 1. In the second case, if we give it a non-number, it does something other than add it to the to the end. But the point about this is that your code can encompass handling the default value, or you can depend on the system to handle it and do other things with your code. It's just, Lisp is a very flexible programming language. There are always lots of ways to do anything. So here we talk about the supplied P, again, for optional and keyword arguments. Optional, small number of non-required arguments that are easy to remember. Keyword arguments, large number of non-required arguments, or ones that are hard to remember. And as I say, really the practical maximum for optional arguments is 3, possibly 4, but you have to start asking yourself why you're not using keyword arguments at that point. There's another kind of optional argument called an and rest argument. It takes after the required arguments any number of arguments you want. You just type them in for as long as you want. The maximum number is probably, I forget what it is, but it's in the thousands, or it may be in the millions for all I know. It's a very large number, more than you would ever practically call things with. So here we have add, and it takes any number of arguments, which are all supposed to be numbers, and what the system does is it takes all of those rest arguments, as they're called, and bundles them up into a list. So the value of the argument numbers, once the function has been called, is a list of all the additional arguments that were supplied. And so here we let sum be 0. We do list n numbers. If no values are supplied, n, it doesn't go through the loop at all. And then we just keep adding the new value. We keep adding the new value to our accumulating value here and setting it. So this is just accumulating all the values, adding them together. And in fact, that's how the function plus works. The function plus takes as many arguments as you want. And the point is, there's no restriction. There's no restriction on the number of arguments you can call it with. Any number of arguments combines all the arguments, single list. Mostly, unless you're doing something where, you know, you're either adding a bunch of things together or you're doing the same thing you could be having maintaining a list of open files, and at a certain point you could you could have a function which will just close all those open files. So you're doing the same thing to everything. That's generally when you use an and rest argument. Now, we've been talking about calling functions by using a form, which is open parentheses, the function name, and then the arguments. But there are two other ways to do it, using other functions within Lisp. And one of those functions is called funcall, obviously short for function call, and it takes the function object and then the arguments. And so the function object is, there are various ways to represent it, but the simplest way to represent it is hash or number sign, quote, then the function name. And that produces a pointer to the function object named by plus. Plus is a symbol, and it has a symbol function slot in its symbols, you know, are complex data structures, and one of the slots they have is called the symbol function slot, and that contains the function object, which is the function named by plus. Hash quote plus is a thing which points to that function object. So here we have funcall, hash quote plus, and then the arguments. And the arguments are exactly the same as would appear in the call to the function here. So if, optional keyword argument, the argument values are just all the same here. And you may notice the power of this, which is funcall is a function that evaluates its arguments, and so this is a way to get the program to decide what function to call based on the environment that it's running in and the values of other things. Whereas, see, when you have a form, open parentheses plus 3, 4, you're always calling the plus function. Here, as it's written here, because this is a constant, the function pointed to by plus, you're still calling the plus function, but as we're about to see, you can actually write a program that will decide on what function to call depending on the status of other values. So, quote slash add is a reference to a function named add, which we defined in a couple of slides back. It's just a variant of plus. So here we have a function called combiner, and it takes an argument, and then it returns a function pointer. If the argument is a list, it returns the pointer to the function list. Otherwise, it returns a pointer to the function plus. So we set the global variable of combiner to the value returned by this combiner function applied to the integer 3. That's going to be, because look at the definition, the type of 3 is a number. It's therefore not a list, and therefore combiner is going to be the function object, the plus function object, and now we can fun call it. Fun call combiner and apply it to the arguments 1, 2, 3, and we get 6. Now, calling a function by its pointer, hash quote plus, if you evaluated that, you would get this expression. This expression can't be typed in, by the way. When you have a hash less than, it means that this is something that can't be read by the Lisp reader. And the reason for that is that it has no way of, it's just too complicated to figure this out. If you actually looked at this, you'd probably get a little bit more data inside that, but we're doing slightly simplified here. So hash quote plus, so fun call, hash quote plus, 3, 4, 5, 6. And then the other method of calling a function is called apply, and it differs from fun call. The first argument's the same, a pointer to the function, but then all of the arguments are bound up in a list. So fun call takes any number of arguments, the first one being a pointer to the function and the remaining being the arguments to the function, however many there are. Apply takes 2 arguments, the first one being the pointer to the function, and the second one being a list of all the arguments. And the advantage of this, of apply, is again, you can programmatically be creating these lists, and so it's easier to use apply when you are determining the function to call programmatically and the argument list programmatically. So here, I'm sorry that this is slightly smaller type, but we had to fit this on the slide. And here we're defining the function combiner, and where type case says, look at the value x, that's the argument, and if it's a number, return the value, the function object plus. If it's a list, return the function object append. And if it's anything else, that's what the T means, return the function object list. So that's what the combiner function does. Now here is the combine function, and it takes any number of arguments, and then it applies the combiner, applied to the first argument, to all the arguments. First of args, remember all the rest arguments are all bundled up into a list, and therefore, the first of them is the first argument, the first rest argument. And so this looks at the first one and says, okay, what kind of object is that? And therefore, what kind of combining function do we want to use? Do we want to add them up because it's a number? Do we want to append them together because they're all lists? Or do we want to just bundle them all up into another list? So if we call combine with the arguments 2 and 3, the first argument is a number, and therefore it adds them up and gets 5. If we call it with arguments which are lists, the list AB, the list CD, the first argument is a list, and therefore the result, it appends them all together. So append takes a bunch of lists and makes a single list with the contents of all the argument lists. So here is a a single list, A, B, C, D, made up of these two argument lists. And finally, if the first argument is something that isn't a number and isn't a list, then it just takes all the arguments and bundles them up into a list, the symbols A, B, and C. Now, notice that we're not doing any testing on the later arguments. And just a comment about this function, if the first argument is a number, all the rest of the arguments had better be numbers, because otherwise plus is going to signal an error, because if it's past a non-number, it objects. And similarly, if the first argument is a list, all the rest of the arguments had better be lists as well, because append can only take list arguments. If the first argument is anything other than a number or a list, it doesn't matter, because list doesn't care what its arguments are. But so you just have to, if you were writing documentation for this function, you would have to say, if the first argument is a number, all the rest of the arguments have to be numbers. If the first argument is a list, all the rest of the arguments have to be lists. If the first argument is anything else, the rest of the arguments can be anything else. There are a number of standard Common Lisp functions which take functions as part of their argument list, and one that we may all be familiar with is sort. And sort takes two required arguments. The first one is something to sort, typically a list, and the second one is a function which is the one that will be used to compare objects. So it takes elements of the list, it compares them using this function, and if the so it passes them in order. It will pass 1 and 4, and if it then does less than 1, 4, if that returns true, it says that the two elements are in the correct order. If it returns nil, as it will with 5 and 1, it says they're in the incorrect order, and it will reorganize those two. So when you're using sort, less than, smallest numbers first, greater than, biggest numbers first, string less than, A before Z, string greater than, Z before A, and let's just go look at that last thing a little bit, just so we can, I'll see some Lisp running here. Let's have a look. Here we go. So you all should see the, yeah, there we go. So there's our debug window, and so let's get a string, which is, you know, EZASDF E. There's a string that's nicely out of order. And let's see, sort. I hope this works. Sequence, yes. String. Now, we've told you that you should use this hash plus, and as I'm about to describe, well, let's just try that. String less than. And so there's ABBFS, that's order, and here's DZ. And the thing about string less than is that it there is some order to capital numbers and lowercase numbers, but it's not actually a defined concept. It's whatever an implementation does. And in Allegro CL, I can never remember the way I find things out by testing them, but apparently uppercase letters precede lowercase letters. And let's, string, by the way, is probably, I don't know what happens to string, actually. No, string's actually the right thing. It destroys its list argument, but I guess it doesn't destroy vector argument. But let's go back to the beginning, and let's sort this using the other thing. And the point I was going to make is, even though you normally do a function object here. You can actually just do the function name as well. That also works for sort and for actually works for fun call and apply as well. Function name or function object. If it gets a function name, it just goes and gets the function object itself. Notice that string less p is case insensitive, and therefore it has put the capital letters in with the lowercase letters depending only on their position in the alphabet for the ordering. And so there we just saw a couple of examples of that using sort. Wrong button there. So here we are back at the slides. And another collection of functions, which we're going to go in a minute, are called map functions. And they map over, in other words, apply some function to all the values in some kind of data structure that has a number of elements like vectors, lists, hash tables, etc. If you do map car hash quote print, meaning the print function, to the list 5146, it will print out each element in order, as we'll see shortly. Now, you can define a function. We've been defining functions using defun that have names, but you're allowed to define a function that doesn't have a name, and that is called, that you use the expression lambda, and that creates what's called an anonymous function. And so here we have lambda xy is multiply x and y, or lambda xy is add x and y. We're setting the value of the variable function to be this function, anonymous function object, and here we're doing fun call of function 3,4. Now, you might ask yourself, what is the function defined? In other words, could we have an expression open parenthesis function, function 3,4? And the answer is no, that would fail. As far as I know, at least so far, the symbol function doesn't have a function defined on it. That's not precisely true because it is a Common Lisp symbol and it does have a function defined, but let's pretend that wasn't true. So we haven't done anything with the function named by function. Instead, we've done something with the variable named by function. And the value of the variable is itself a function object, in fact, an unnamed function object. And so the value of the variable is something suitable to being passed the fun call. So if you try just the last two forms, we just gave two definitions here, but this is the one that's working since it was the second one, is going to add these two values, 3 and 4. So the mapcar function takes a function object. Here's the typical use of lambda. You're calling mapcar. Mapcar takes a function object and one or more lists, and it applies the function to the cars of all the lists, the first elements of all the lists, and the second elements of all the lists, and so on. So here we have a function which takes an argument, adds 1 to it, and we're calling mapcar with that anonymous function, and numbers is a bunch of numbers we added here. So increment all, 5, 6, 7, 8. It goes, so it's a rest argument. Those are all bundled into a list. And so numbers is then a list, and the mapcar function applies this function to each element of the list in order, bundles all the results up into a list, and returns it. So increment all works this way. All those numbers, and you end up with a list with one greater than all of the arguments. But the point is that this is where you use an anonymous function. You're defining a function on the fly. There is no point. The function is remembered in this definition. There is no point in you defining a specific function called add1to and using up resources for that purpose, because you're only using this function in this definition here. So when a function you'll have has only one caller and is relatively trivial, it saves using your namespace. You're not giving it a name, so you're not using the resources of giving it a name. The code in place may improve readability in some situations, and it's commonly used with mapping functions, sort functions, and things like that where the function is part of the call. Now, what do we mean the code in place? This definition of increment all, the function definition's right there. If you're looking at this source code, all the information you need to see what this function does is right there. If you defined a separate function called add1to, and this was hash quote add1to, then you would have to go look for the source of that function, wherever it was, in order to understand exactly what was doing. Instead, we have the complete definition right here. So that's what this third bullet is talking about. So there are other tools once you've got functions defined to investigate things. So one question is a symbol have a function definition? And the function fboundp applied to a symbol returns non-nil. In fact, it returns the function object if the symbol does name a function, otherwise it returns nil. And this is a convenient way to discover whether functions have been defined on symbols. Like many predicate functions, it's not going to signal an error if the function isn't defined. There are other operations where you could extract the function, but if there is no function defined, then you might get an error or it might complain. But fboundp just returns the function object, which is a non-nil value, or it returns nil. There's fdefinition also retrieves the function object. When the argument's a symbol, it's exactly the same as fboundp, and it, I'm sorry, it's exactly the same as symbol function. Let me, let's go look at, I just don't remember something about this, so let's figure it out. So we define foo to be a function that adds 1 to its arguments. And so fbound p of foo and fbound p of bar. Bar has no function definition, so fbound p returns nil. Now let's look at fdefinition of foo. And again, we get the thing. Now, what about fdefinition of bar? I don't actually know the answer. The question is it going to return nil or is it going to signal an error? And the answer is it signals an error. So the difference you see here is the important thing about fboundp. It doesn't signal an error if there's no definition on the symbol which is passed as an argument. But fdefinition assumes that the symbol you're passing it does have a function definition. Now, what about symbol function? See, a lot of ways to figure out how things work in Lisp is just to test them. Also, signals an error. In other words, the bar, the argument symbol must have a function definition in order to call symbol function. What am I doing here? It was shift. Let's try return. There we go. But if we do this with foo, where's the... you see symbol function applied to foo returns our nice interpretive function foo. So that's what I wondered about, and now I know. Both fdefinition and symbol function only work when the argument symbols actually have a definition, function definition. If they don't have a function definition, then they will signal an error. So one of the uses of fboundp is you could do if fboundp quote foo, fdefinition quote foo. That's going to return nil if there's no function definition and the function object if there is. The reason that the difference between fdefinition and symbol function is that fdefinition also works on function names which are lists. And we don't go into these a lot, but it is legal to have a list as a function name. And in standard Common Lisp, the only kind of list which is legal is one where the first element is setf and the second one is a symbol naming a function. In Allegro CL, we actually allow more lists, but it's pretty uncommon to use them. And this is the only one. The setf foo list is kind of list is the only one that's used. We'll see a couple of examples of that later. There's also a function called function Lambda expression. It takes a function object, not a function name, as an argument, and it returns the definition, that is the source, if as a list, as what basically mostly what appeared in the defun. Let's I'll just show you that. So we have some function definitions. So let's go. I've forgotten the name of the argument. Function. Is that it? No. What is it? Symbol function definition. Something like that. Oh, I'm sorry. Can't remember anything. Let's just go back and look at what it was. Oh, yes, function Lambda expression. I so rarely use this function, can't remember its name. That's what we want. Function LA, and then I hit Control dot, and it fills it in. Hash quote foo. And there you are. That's kind of looks like the defun, except not entirely, because it's modified it for the way the well, it sort of looks like the defun. In fact, except it's turned it into an anonymous lambda. The fact of the matter is this function isn't particularly useful, and I like to mention that because people run into it and think it might be useful, but it's not. It won't work on functions where the code where they weren't defined, where they where they were loaded in a list already compiled, and if it's one of your functions which you've defined, well, you define it. Go look at the sources that they're your sources. You have them. So even though this looks like a useful function, in fact, it's not. Now, there's a function called fmacunbound, which takes a symbol argument and removes the function definition. After you have done this, add no longer names the function. And there's also a function called macunbound, which makes a variable have no value. And occasionally, you're always, if you've managed to mess things up in your function definition, you can always get rid of it like this. The function symbol function returns a symbol's function definition, or the function associated with it. As we saw, remember, it will signal an error if the symbol does not name a function. And you can also use setf to set the function named by a symbol. So setf, symbol function of double, and here we define a anonymous function object. And so now double names a function, and this is the function it names. And in fact, if you take a defun form and macro expand it, defun is a macro, you macro expand it, you'll discover that buried inside quite a lot of code, well, you know, nothing better than actually so the function macro expand can always be used when there is a macro, and let's go up and capture the definition of foo up here. You hit return and it brings the definition down. So there we are, macro expand of defun of foo. And okay, it's a whole bunch of stuff, but what's all this beginning stuff? Well, it's making sure that you're doing the right thing, and so here's make sure that there isn't any definition locks on it, and it stores things in some local variable for, some global value list here for God knows what reason. This is all having to do with internals of the system and the compiler. Those double quotes mean that these things are internal variables or internal symbols, and therefore not ones that are available for users. And, I don't know, a whole bunch of other stuff. Finally, we get down to setf of f definition foo, and here is the argument list itself. And this hash here is, let's see if we can p-print. Whenever you have a list where you get a hash like that, you always call p-print. Yeah, there it is. That's, see, it was excl : f, and then, so here we are, name function foo, lambda, block foo. There's the code, adds 1 to x. There's the argument x. So the point of all this was that buried deep within the code that's actually called when you call the fun is a setf. It's actually a setf of the f definition rather than a symbol function. But remember, they're essentially equivalent, except f definition also works on different kinds of function names. So the fun and setf of f definition or f symbol function, they act globally. They define a function on a symbol, and that function is now available when that symbol is used as the function name anywhere within the list. But you can also define functions locally using the one of these is macro, one of them is special operator, flet, and labels. Now, flet, actually the name, if you're familiar with let, sounds right. This is sort of a function let. Labels, I have no idea where the name came from. Labels is essentially like let star. And the point of it, we're not actually making use of it, but is that you can define a number of functions and the later functions can refer to the earlier ones. If you used flet, each function is defined separately and the ones defined later can't refer to the earlier ones. So what does the call the labels look like? So it is a list of function bindings. So the beginning of the list is there, the end of the list is there. So here is the first element of the list, and it just looks like what follows defun. That is, we leave out the word defun, but here's the symbol naming the local function. Here's the argument, LST, and here's the body of the code. And then if we went down, here's the body of the labels form, and it prints third applied to the third is the rest of the list is all the elements of the list except the first element. Rest of that, we're now down to all the elements of the list except the first two elements. First of that takes the first element of that result, so we're getting the third element of the argument list here. And so if this is going to print 3 and this is going to print C. Anyway, the point of this is a local function definition. When you have come out of the labels form, the symbol third won't have a function definition, assuming it didn't have one going in. Just like when you come out of a let form, the local variables that you gave values to don't have values unless they had values before. A setf function is useful when you have a pair of operations for getting and setting a value. And often in C or other languages, you get pairs of functions called get whatever and set whatever. With setf, you only have one function name. So when you have a function which accesses a value from a data structure, setf of that function will replace the value in that data structure. The function first takes a list argument and accesses the first element of the list. Setf of first of list accesses the first element of the list and replaces it with this new value. Setf is a macro, by the way. You can always macro expand it and see what's going on. although unfortunately in most cases it macro expands to internal functions. So here is a function named first, and it takes a list argument and takes its car, so this is getting the first element of the list. Now, we define the setf function as first, and here we're doing a definition, defun, and the name of the function is a list. And you see, not a symbol, but a list, and this is one of the allowable lists. And so it takes two arguments, the new value and the list, and then it calls replaca, which is a function which takes a list argument and replaces the first value with the new value here. And then it returns the new value. That's what setf functions typically do, is they return the new value. So we see this in operation. Here, A is the list containing 1, 2, 3. If we apply our first function, that's a 1, first function to A, we get the first element, 1. If we setf the first of A to be 1, that call, which is calling the function we've defined, this setf function here, so first of A is now 1, and now A is 1, 2, 3. Let's just go look at that a little bit more in the Lisp itself. So we define first to be the car of X. And so first of A, B, C should be A, as it is. And then we define setf of first on the argument list new and list to be replaca. Now, what does see up here? There are the arguments. So we need the list first, and then the new value, and then we return new. So if we do setf of, let's get a, so here's our list with the values 1, 2, 3. It's the value of the variable r. So first of r is 1, and if we do setf of 1 r, first of r to 1, r is now the number 1, 2, 3. If we do setf, if we can also call it this way. Now, what's the argument list? Oh, it doesn't know. It didn't remember, but it's the new value. Let's give it the value 4, and this should work. Oh, it didn't. Now, I'm sorry. I always thought that did work, but I guess it didn't. Anyway, when you've done the setf definition like that, let's try one more thing just for fun. It may not work either. No, neither of them worked. Okay, so when you've done that setf definition, then you have to call it in this form, setf of first of r being the new value. And that's there we go. So here we are back there, and as you see, that modifies the thing as I just showed. Now, setf will work on a bunch of predefined list functions, all the ones for accessing elements of lists, first, second, third, through 10th, last, nth, elt, which works on a sequence, that is with a vector or a list. and will work on aref and fill pointer and a whole bunch of things associated with arrays. It will work on elements or fields of a structure, swaps of a CLOS object, symbol value, as we saw, symbol function. Symbol value is the thing that's the value of the variable. Symbol function is the function is named by the variable. Also works on get hash. So the way that you set a value in a hash table is doing a setf of get hash of the value. We're going to do hash tables in a minute. So a lot of things are setf enabled, and so this is the way that you actually can modify the values of predefined data structures is by using setf and these various accessor functions. So now let's go through mapping functions. We saw an example of a mapping function before, just briefly when we were showing passing function objects around. So the idea of a mapping function is you pass a pointer to the function, and actually the function name works as well, but it's always better to do hash quote the function name. Pass a pointer to the function of one of the arguments. The pointer to the function is applied to each element of the collection. The other arguments are usually a bunch of lists or a bunch of data structures of some kind. The result of individual calls may be collected up into a list. So mapcar takes a function and then at least one list and then as many more lists as you want. And what it does is that it applies the function to the first argument of the list and the first, I'm sorry, not the first element of the list and the first element of all the rest of the lists. And then it applies it to the second element of the list and the second element of all the rest of the lists. And so on until it reaches the end of the list. And it does what you expect if the lists are of different lengths, which is it stops when it comes to the end of the shortest list. So here's a simple call to mapcar. The function is print. There's only one list, and it applies print to the first element, then the second element, and the third element. Prints A, prints B, prints C. Here we've got two lists. The function is cons, and it's applied to A and 1, and then B and 2, and then C and 3. And the other thing that map does is it bundles up the results into a list, and that is returned. And here is the returned list of A, B, and C. Remember, it's what's returned by the function, and print functions return what they return what they print. That is, print C, and print 1 all return what they print. So printed the symbol A, returned the symbol A. And cons returns the result of applying cons to A and 1, and that is the dotted list A.1. So this ends up being the list of these three dotted lists. There are a whole bunch of map functions, and we're not going to go through them except for this additional one. You just have to go look at them, and when you are doing things to one or a bunch of lists, the map functions are useful, and so if that's what you're trying to do, you go look at them all and figure out which are the ones that are most useful to achieving what you're trying to achieve. Now, the do list iteration form you can often write a do list form that will do the same thing as your mapcar or your mapping functions are doing. The thing is that the mapping functions are already defined and save you a bit of coding. Another map function which is important is map hash, which applies the function to every key value pair in a hash table. And we're just mentioning it now. We're going to discuss hash tables a little bit later today, and then we'll see an example of map hash in action. Another concept is multiple values. Most of what we've been seeing are functions that return a single value. But you can actually have a function return more than one value by using the values I think it's a special operator. So suppose that you're interested in more than one value being returned. Then one thing to do is you can bundle all the values up into a list and then return the list. And the calling function can then extract the various values to, one by one as you need them by using the list extraction functions like first and second and so on. The other thing is that you can call values and have as its arguments all the things you want to return, and then the function will return all of those values as multiple values. The first one being called, unsurprisingly, the first return value or the first value, the second one being the second value, 2 is the second value, and you can have as many as you like. So there could be a third value, fourth value, fifth value, and so on. Now, how do you capture these multiple return values? Well, there are a bunch of functions, and one of them we're going to describe here is multiple value setq. There's also multiple value list, which bundles them up into a list, and multiple value bind, which binds them to variables rather than globally setting them to variables. And use it like setq to capture multiple values. So here, we're doing a let form. We have local variables x and y, both initialized to 0. We print them out. Print x, prints out 0. Print y, prints out 0. Now, we call foo, and we use multiple value setq. The first argument is a list of symbols, or list of variables whose values will be set to the return values of this function. Foo returns 2 values, so x will be set to the first one, 1, and y will be set to the second one, 2. And when we then do print x and print y, x will be 1 and y will be 2. If there are more values than are returned, the additional values, the more variables than values returned, the additional variables will be set to nil. If there are more values returned than there are variables, the additional values returned will be ignored. If you do, well, let's go look at this, because this is actually useful. Let me just show you a couple of these in lists. So, multiple value, and let's just do a control dot here. What did I spell wrong? Oh, I can't spell multiple. That's the problem. Multiple, that looks better. And control dot. And you should all see this little menu that comes up when in the IDE, when you hit control, hold it down, and then hit period, you get a little menu. Well, it completes the symbol name if it knows how to do it. Otherwise, it gives you a menu of the various things. And I just wanted to show you all the different functions defined which have multiple value as a start. Now, I'm just going to click away from that because I just want to show you. Let's go SE, and then I hit control dot. It fills it out to multiple value set Q. A and B, and now use 1, 2, and 3. So there are 3 return values, and now A is 1 and B is 2. If we did this and only had 1 value, so A is 10 and B is 0, because we did set it. There was only 1 value returned, so all the additional variables get the value 0. Now, if you just set a value to B, so we're doing set to R, and then we're doing values 1, 2, 3. R is now 1, the first return value. The second and third return values are ignored if they're not used. And when you have a function that returns multiple values, see, they all get printed out there, 1, 2, 3. Star which always is the last value, is always the first. The second and third return values, by this time you've got to this prompt, have been forgotten. You have to capture them. So let's just look at multiple value list. And so this time, let's see, get a C there. And values 1, 2, 3 bundles up all the return values into a list. Okay. Multiple value bind, same thing, except it does makes these local variables. So it's like let star. It captures the values as local variables. Again, if there are more variables than values, the additional local variables get set to nil. Okay, now we're going to discuss, and if you have any questions, by all means ask them, but we're moving on to discussing some additional data structures within Lisp. Tomorrow, one of the most important additional data structures within Lisp are CLOS classes and instances of CLOS classes, and we're going to spend essentially all of tomorrow, that we're not catching up on what we haven't done today, on those. But today, right now, we're going to discuss structures and hash tables. Now, structures are similar to what are available in other languages. They are user-defined data structures that contain slots, and the slots contain values, and they have various options for controlling how they're accessed. CLOS instances and classes are one way to do a user-defined structure, and we're going to discuss those tomorrow. Yeah, when I say tomorrow, of course, Jaime's completely correct. I mean the next session, which is next week. Yes, I'm sorry. We're going to discuss those in the second session, which is to say next week. CLOS instances, we're going to discuss then. Def structs are what we're going to discuss now. Both of them store data in a user-defined format. Instances can have behavior in addition, and def structs are more efficient but less powerful than CLOS classes and instances. Slot references and so on look similar, but there are certain more complicated things you can't do with structures you can do with CLOS instances. So you define a structure with a defining macro called def struct. When you call a def struct, it automatically defines a number of auxiliary functions. It defines a maker function whose name is make hyphen the name of the structure. And when you call it, it will create an instance of the structure. And as arguments, you can specify values for various slots. And it defines a number of accessors which all have the structure name hyphen slot name. And so, will access, when you have an instance of the structure, will access the value of that slot, and you can also use setf with it to set the value of that slot. So here we have def struct. I'm sorry for the small type. Def struct route segment, and it has the following slots, which are just simply listed: node number, start, and end. And so it returns the name of the structure. So here we create one. Make routes segment. Make route segments automatically. That's the maker function which has been automatically defined. And it comes with keyword arguments for each of the slots. Named, the keyword arguments are in the default named by the slot name. So here we are specifying node number and giving it 5, start 2, end 7. So here's the structure, and it actually prints out lots of information. And now we can access the road segment start of this instance of a route segment structure, and it's 2 because that's what we defined it to be. Now, we didn't define any default values. We specified all the values here. If you don't specify a value, I think we would have got nil, or but if you want to give slots default values, you can define them much in the same way that you give optional or keyword arguments default values, with the slot name followed by the default value. So here we're defining a structure point, and we create an instance of point by calling make point. We're not giving it any arguments, and the X and Y slots are given the default values 0 and 0. We could have said make point colon X 10, then X would have been 10, and Y still would have been the default 0. Now, standard structures within Lisp are in fact implemented as vectors. Accessing an element of a structure is quite fast because it only has to do two things. It's got to look at the element name and figure out the displacement in the vector, and then, three things, and then access that element of the vector. And vector operations within Lisp are very fast. The reader functions get compiled into vector access functions, and because we know everything that's needed to know about them, they're very fast. So when you have an accessor, say, to the Y slot, it's going to be called point-y, and when you compile that function, the system is going to know what the point structure looks like, and so the offset will be built into that function, and the function will be completely optimized, and so the access will be very fast. But one thing about this is that if you redefine the position structure, say so it has 3 slots, or so that the Y slot is renamed something else or something, you've got to be sure to recompile all the code which makes any use of the accessor or maker functions in order that the new definitions will be seen. Because the accessor functions will very likely be compiled in line. That is, they won't see a specific call to point Y. Say you have a function foo that takes a a point structure as an argument and then accesses the Y value. When you compile foo, the call to point Y actually will disappear, and it will simply write machine code that will do the right thing. Therefore, if you redefine point Y, that redefinition won't be seen until you recompile your call to the function foo, recompile the definition of foo. So you can also say, well, I don't want it implemented as a vector, I want it implemented as a list, there may be reasons to do that, but just showing you what your options are. Then if you're implementing as a list, you notice it's only giving you the slot values, but you can tell it, now I want it named as well, in which case it gives you the structure name and the slot values. You don't normally implement structures as lists, and so this is just kind of information on what's possible. That's about all we're going to say about structures, because for the most part you'll be using CLOS classes and objects, and you really only use structures when you've got things that are very elementary and you're going to be accessing them a lot of times, so you want it to be fast. Now, hash tables are, there's a lot of data within lists, and a lot of data that you have, which is, you have what's called a key and then a value. So imagine a dictionary. The key is the word being defined, and the value is the definition. Imagine a set of employee records. The key is the employee name or possibly the employee number, and the value is the employee data, a big list or structure or CLOS instance of employee data. So the question is, how do you store this information in such a way that it is quickly accessible? Now, one thing is, let's say you could have a list, and the list could have, let's say you're doing a dictionary, and the list could be the word, and then the second element, the first element's the first word, the second element's the definition, the third element's the word, the second word, the fourth element's the second definition. okay, so you've got this, and there are 100,000 words, and so you've got 200,000 elements in the list, and you want to find the definition of the word zoo, Z-O-O. Let's assume they're in alphabetical order. Well, you start at the beginning, and you're at aardvark, and zoo is almost, at 999,090. So you're starting at the beginning of the list, and you're going through 999,090 elements, and then you come to zoo, and you find the definition. Well, that was an awful lot of work. You just were going through the list, doing a lot of comparisons, and it took you a lot of time to get there. All right, suppose your dictionary is static, and so you have a vector, actually two vectors. And the first vector is the list, contains all the words, and the second vector contains, all the definitions. But anyway, your problem is, how do I find where zoo is? Well, since it's a vector, it's got 100,000 elements. You might make a guess that, well, Z is, maybe I'll start at 900,000, and, 90,000. And then you look at 90,000 and you find that's, victory. And you say, okay, that's a V, I've got to go along. Anyway, you can do a search algorithm and you'll eventually find it. But the point of both of these methods are really inefficient because you're basically searching on all the keys until you find the right key. And then you can go find the value. Now, the thing about the hash table is that it takes up a lot of space in memory, a lot of disk space, and it populates the keys and values in this great deal of disk space, but it does it in such a way that it can take a key and applies a function to it called a hash function, and that tells it where to look. And if you have a well-designed hash table where two different keys don't give the same value, then you can find an element of a hash table by simply doing an application of the hash function and then jumping to a location. And both of those are very fast functions. Even if you have some collisions, that is where the same keys return the same hash value, and there's a little flag that's set that says that they do that, you still don't have very many places to look. You just have to go, in that case, it stores a list of the possibilities for what are called collisions, and then you go look in that list, and you're still looking at only a few number of places, not like a list where you had to go through 990,000 values. And by the way, with a list, you're always going through those values because to get to the 99,090th value, you had to start at the beginning of the list and traverse the whole thing anyway. With a vector, it's a bit faster, but you're still doing something like a binary search. With a hash table, you essentially go right there. And you pay for this by using more disk space. But disk space is cheap. That's why we don't care. Pair-oriented associates keys with values, just like A lists or P lists, or you can do that with vectors as well. Could use generally hash tables. You see, you can use a list when you don't have many elements, but the searching time within a list grows proportional to the size of the list. And so if it takes 1,000,000 times longer to find an element in a 1,000,000-element list than to find an element in a, 1-element list, which of course doesn't take much time, but to find an element in a 10-element list takes 100,000 times longer. Hash tables compute the hash function and use as an index, and the speed is largely independent of size. Now, the thing is that Lisp provides a great deal of support for hash tables, and other languages, often you have to implement them yourself. So you create a hash table with the function makeHashTable. You use the getHash function to access. You pass it a key and the hash table as arguments, and it returns the value associated with the key, and it returns two values. If the first value is nil, how do you, I mean, it returns nil if that key does not appear and there is no associated value. The key value pair doesn't appear. Well, how can you tell the difference between color appearing and having the value nil and color not appearing at all? Well, the second return value tells you whether the key has an associated value. So nil means that color does not appear in the hash table. And therefore, the first nil means when you get two nils, that means the object, the key, does not appear in the hash table. Now, you can use setf of getHash. There's the same form, getHash, and you can give it a value. We're giving it the value brown. And so once we've done that, we do getHash of color of the hash table, and we get out the associated value brown. And we get the second return value being T, meaning it was found. Suppose we've done the set, well, let's actually, let me just go show you that, because this is a very important point. So we create a hash table. Now, there are a bunch of arguments to make hash table, but they're all keyword arguments. They don't need to be specified, so we start out. So get hash color. And it's not there. Now we do setf, and we can drop this one down like that, and let it give it the value nil. Perfectly reasonable value. Now we look at that, and what am I doing here? Let's see. There we go. Now we get nil. That's the value associated with color. But the second return value is T, indicating it was there. The nil is its value. It's not indicating that the hash table didn't have this. And, of course, we can give it any value we like. We can reset it to be brown. All right, better put a quote there or it's going to fail. There we go. And now when we get the hash value, we get like that. That's just what we expected. But I wanted to emphasize that nil point, what the second return value was telling you. GetHash returns two values as we described, so I just went through all that. Hash table functions. There's a function which tells you whether an object's a hash table. GetHash gets the Jaime, I'm not quite sure what you mean. Sort of unmute and is what returned as a list?
Is what when you say get hash color HT, okay? It returns brown and T. Can you consider brown and T together to be a list, or is it just
no? It's returning multiple values.
Just multiple values.
If you want to capture them both, you have to do multiple value set Q and one of the multiple value things. Let me just show you that quickly.
Thank you.
Yeah, I just want to show you how that's done. So, I learned to spell value set Q, and we're going to do val and there, and let's do get hash. And so now val has the value brown, and there has the value T. So if you need to look at the second value, you have to capture it with one of the multiple value functions. And there are several of them, as I said, and that's just one example where you do that. And so you might then say, you see, let me just do this. First of all, let's get the value to be nil again. And now we do multiple value bind. And V and T and get hash, where is it? There we go. Okay, so you would do something like if v, that is, if the first return value is non-nil, and then otherwise, if t so okay, what did I do? V. Oh, all right. Sorry. Let me just do that again and make sure I've got the right. What are the arguments like? Rest binding values 1 and value. Well, that should work. That's embarrassing. Why isn't it working? Oh, I understand. It's objecting to. It might be objecting to that. Let's see. Yeah, it's still whinging about something. Anyway, that's what I was trying to do. Where if you take if the value's there, you return it. If it's nil, then you look at the second value and tell you whether it had something or not. And I'll get that right later, but I want to go on with the slides. So I'll show you a corrected of that version later. So here we just doing the examples like I've just done. There's a function called clear hash. It just clears all the elements from the hash table. And here is the call to map hash. Here's a function that simply prints out information, and it goes through all the key value pairs. And so you can look at this example on the slides. It's just an example. Map hash is something, as I say, that maps through an entire hash table, iterates over all the contents. Just a quick, I want to get to macros today, at least in the beginning, and so we're just going to go through bits and bytes quickly, but there's not a lot to say about them. They just, So bits and bytes are represented as integers. They are often efficient, and they're often used in combination with foreign function calls. So you can define an object to be a byte, and then it will can have a value up to the size of a byte. Obviously, a bit can only have values 0 and 1. You can the reader macro hash b reads its elements as if they were a binary number. So hash b10 is reading 10 as a binary number. When you evaluate it, it gets 2 because printout is done in decimal, and that is the binary number representation of the decimal number 2. There's a function, there's a variable called printbase, and printbase always returns 10 because what the value of printbase is the base in which you are printing integers. And of course, the base in which you are printing integers, if you print that value, it's always 10. So it's not really telling us it's 10. You'd have to do some more analysis to tell if it was 10. Read base, by the way, is always 10. So print base is it's not telling, but trust us, it always starts out at 10. Here we are binding it to 2, and then we are printing this binary number, and it comes out as 10 because in the context of this, in the scope of this let binding, the print is being evaluated, so that's how it's working. So that's the decimal integer 2 printed as 10. There are a whole bunch of functions like log IOR and log AND, which combine bits of integers, and it combines them in a bit-by-bit fashion. So log IOR, the result has a 1 if either of them were a 1, and a 0 if they were both 0. Log AND has a 1 if they were both 1s, and a 0 if either of them were 0. And then there are a whole bunch more of log XOR is a 1 if one but not the other is 1 and 0 otherwise. Log and so on. Just go look up the definitions. These are the two that are most commonly used, and there's another one called log test, which takes a binary number and an index and tells you whether the bit at that index is 1 or 0. Yeah, here's log test. So true if the second or flags is one binary number and mask is another binary number, and log test does the log and of the two things and returns true if it's non-zero and nil if it's 0. Log bit p returns 1 as, remember, list is 0 index, so this is the second bit. Returns 1 if the second bit is 1, otherwise returns nil. Log count counts the number of bits that are on, counts the number of ones. Byte manipulation, there is a function called load deposit byte, or LDB. It takes a byte specification. The byte specification says 4 bits starting at bit 0, or 4 bits starting at bit 4, or 8 bits starting at bit 0. So the first argument to the function, to the byte specification, the function byte, is the number of bits. The second is the starting bit. And here is the value flags, which is a bunch of, let's see, 3 1s, 3 0s, 3 1s. And so you evaluate these things, and you get the lowest 4 bits, which are 0, 1, 1, 1, or 1, 1, 1. That's what we get. I don't know if the 0 is always printed. Or we get the next 4 bits, which are 1, 1, 0, 0, or we get the lowest 8 bits, which are, 1. Let's see, 1, 1, I guess. Yeah, 0, 0, 0, 1, 1, 1. So you can use setf with LDB to replace bits. And there is a function called ash, which takes an integer and moves it that number of bits over. So you take 1, you move it 10 bits over, you get 1024, which is 2 to the 10th. And here you can have a negative number there, and it will move bits to the right. And if you exceed the number of bits, the result's 0. No assumption of integer size. You might get a big number if you keep shifting left. You shift left with a positive. And it, as you shift left, it adds zeros on the right-hand side. It doesn't add 1. Here's an example. Integer length is similar to log count. It is the number of, it's analogous in some ways. It's the number of bits required to represent a particular integer. And sometimes that's a useful piece of information. And here's an example using it. Vectors of bits, you can specify the element type to be a bit, and then you can you can set values to the initial element 0, you can set values to be 1, but you've specified the element type to be a bit. The only values you can give it are 0 and 1. Obviously, those are the only legal values. Okay, we're just have about 15 minutes left, and we have about 60 slides, so I'm going to get through probably 15 to 20 of the slides, and we'll be in the middle of macros, and we'll just finish up macros next week. So it's a longish subject. This, as I say, the first day is a little unbalanced, and so we didn't completely expect to finish the first day and actually cover the material in a useful way. So let's just get right into macros. A macro takes a list form as input and returns a separate list form as output. And there are a lot of macros already defined within lists that we're used to. Defun is a macro. Incf, which takes its argument and increments it by 1, is a macro. Setf is a macro. Setq is not a macro. It's just called a special operator. And that is kind of a primitive within lists from which everything else is defined. There are several dozen special operators, and in a sense, everything else is defined from them. So anyway, you define a macro with a defining form. There are a whole bunch of defining forms within Lisp. They almost all start with the letters DEF. Defun defines a function. Def macro defines a macro. We earlier saw def struct, which defines a structure, etc. So here's the name. Here's the argument list. And here is the body. So when it sees incf, now this is actually a standard Common Lisp macro, which we're not supposed to redefine. So if you actually tried to evaluate this, it would complain that you were defining a standard Common Lisp macro, and you're not allowed to do that. If you want to try this, just give it a different name, like my incf or something. So, but if we were implementing Common Lisp ourselves, this is what we would do. It takes a call that looks like incf A, and it transforms it into setf place, which is x, that's the argument, to list of plus 1 and x. And I think that's what, yeah, so when the evaluator sees a call, once that macro has been defined that way, to incf of A, it says, oh, incf's a macro. And then instead of treating this like a function call, it treats it like a macro call. It finds the rules that you have just given for macro expanding the form, and then it applies those rules, and it transforms incf A into this list, setf A to plus 1A. And then that's the expression that it evaluates. So when you call a macro, the first step is to macro expand it into a different list form, and then the second step is to evaluate that list form as if that was what you had typed in. So yes, if you type in incf A, it's as if you had typed that. Macro evaluation is different from function evaluation. With a function, when it sees that the first argument of the first element of the list names a function, it first of all does and goes off and finds that function object. Once it's done that, it then looks at all the arguments, which are the next elements of the list. This is the system we're talking about with the list reader, and it evaluates those arguments, all of them, one at a time. It then applies the function object, which it has retrieved, to the evaluated arguments. For macros, it passes the arguments without evaluating them. The macro function then returns a different expression, and then the evaluator evaluates that expression instead of the original one you typed in. Macros can expand into other macros, so that if, I hope this is true, but you can try it, if you have a when form, it expands into a cond form. Cond is also a macro. Cond then expands into an if form. The evaluator and also the compiler recursively macro expand things until there are no macros left to expand. Macro expand is the function Lisp uses to call macro function to get the results, and this statement isn't quite true. It doesn't. It does a lot of macro expanding, but it doesn't macro expand everything until under some circumstances. Sometimes buried within things in positions where it's not expecting to see things, you'll still have macros around, and you've got to work on them separately. Macro expand 1 just does one step of the macro expansion. Here's macro expand 1, but that's the whole macro expansion because there's nothing more to do. But you can always use macro expand and macro expand 1, and we recommend that you do this to list macros that are defined so that you get a feeling for what the definitions look like. Now, we did that to defun earlier today, and often you end up with a lot of stuff you're not going to understand because it's internal, particularly for something so fundamental as defining a function. Other times, like if you did this macro expansion, you'll end up with Lisp code which is very easy to understand. Now, when an object is defined, when a symbol, the operator on a symbol is defined to be a macro, the what is created is what's called a macro expansion function, or a macro function. And that is what is stored in the symbol function slot of the symbol. So it uses the same slot. It has a different, or either the macro function is encoded in a particular way, or there's a separate slot of the symbol that says this is really a macro and not an ordinary function. And so when you call the function macro function applied to a symbol, it returns nil if the symbol has a normal function definition or no function definition. Macro function will actually not signal an error if the symbol doesn't have a function definition, but it will return the function object, the function which is the macro expansion function, if the symbol names a macro. So macro function is not only a way to access the macro expansion function, it is also a predicate function that will tell you whether a symbol names a macro or not. So here we have a number of macro definitions. Here we have the macro nil bang, or exclamation point, and it turns into, it takes a symbol as an argument, and it turns into setf, well, it takes actually a place as an argument, so let's assume symbols are places, and it converts a call into setf x nil. So we can set x to 5, and then we do nil bang x, and x is changed to nil. If we macro expand the call nil bang x, it comes out as to what we told it to come out to. Now, in all of these cases, we're using the list function, and we're doing a bunch of quotes there, and the arguments, when we want them evaluated, are being evaluated. So it's quote setf. That actually makes the macro source functions somewhat more difficult to read. So there is another operator within Lisp, or reader macro, a special character within Lisp called a backquote. And the backquote on most keyboards is in the upper left, under the tilde. The regular quote, or the forward quote, is the one that's right by the Enter key on most keyboards. Your keyboard, of course, may be different, but that's where it is on both of the ones that are in front of me. So I think that's pretty common. When you see it goes before a list in the same way that a forward quote would go, and it protects the list from being evaluated just as a forward quote does, but you can use a comma to unprotect particular elements. And so here we're setting the value of A to be 1 and the value of B to be 2. So here is the back-quoted list. A is comma A, B is comma B. And when it evaluates that, it comes out as the symbol A right there, still protected, is protected, comma A, unprotected, so it takes the value of A. B is comma B, unprotected, so it takes the value of B. Now, here is our redefinition of the incf macro. Takes a place and back quote, open parenthesis, then setf, protected, comma place, meaning we evaluate the argument place, and therefore get whatever is actually passed to the incf macro. Open parenthesis plus 1, all of those are protected. The 1 doesn't need protection, evaluates to itself, but if we put a comma there, it wouldn't make any difference. But the open parenthesis plus certainly needs protection. And then comma place again. So this is the same as, this definition is the same as this definition. It's just in some ways this one's easier to read because it is closer to what the actual result is going to be. Now, there's also comma @ sign. It splices in a list. So when you get, here are the numbers, comma list. So here are the value of LST is this list, 1, 2, 3, 4. Here are the numbers, and then it prints out the list. If it's comma @ sign list, it removes the parentheses from the left and right. here are the numbers 1, 2, 3, 4. Within the definition of a macro, you often have an argument which is called a body argument. In fact, a body argument works exactly like a rest argument, but it is typically reserved for macros, and that's because, and what it is within the macro definition, this is kind of the body of the definition where the work is actually done. Like when we're defining a function, we talk about the argument list and the declarations and the documentation string, and then the body of the function. So this is where you put the forms that are going to become the body of the transformed macro. Many macros are defined with are named with beginning with the word with, and that basically is saying that you are with, and then you have some binding list, and it says with this setup, execute this body. So here we have with, and then notice there's a double parenthesis there. That means that the call to the macro, the first argument is going to be a list, and the list is defined by this argument list. That is, the list has to have at least one element and optionally have two elements. So, and then it's going to have a body, and here is the work of the macro. You're going to do the back quote, let var be val, and execute the body. See, we're unbundling, body is going to come out as a list, and we're unbundling it there. So when we call with a print A, if we macro expanded that, it would macro expand into let A be nil, print A. If, because val is optional, specified to be nil. If we called this with A2 inside that parenthesis, it would be let A be 2, and again, print A. So we're calling with a bunch of arguments. The body is these forms here that are actually going to do the work. Here are the instructions for the macro expansion. And with open file is a macro which is already defined within list. It's the one that will open a file, do some stuff with the file, and then close the file. And so this is what the definition of with open file could look like. Again, you can't evaluate this because it will complain that you're trying to redefine a list operator. If you want to try evaluating this, just give it a slightly different name, like with open file -1. Actually, I think that one's probably defined too, but you know, with open file mine or something. And so here's what it looks like. Notice the argument list is going to be bundled, is going to be within a list in the call. Here's the variable. There are a whole bunch of additional arguments, which are the arguments to open. Then there's the body. And so you bind the variable to the what open returns when passed all of these arguments. Here we've unbundled the rest list. That's what the comma @ sign is doing. Then we do an unwind protect, which we're going to talk about later, but basically says if there's an error, just get out of this thing and make sure that you close the stream, which is basically what it's telling you to do. And then it runs the body, and then if the stream is, if this is a stream, close it. Never an error to close the stream which is already closed, I don't think. Unwind protect, we'll talk about it later on, but it ensures that this final form is run even if there's an error within this body before it throws you into the debugger. Okay, let me just do one more slide just to show you. There are a whole bunch of macro examples. So you can just look at these slides and look at these examples. Push last adds to the end of the list rather than the beginning of the list. And I think, so we're at slide 86 in the middle of macro definitions, and that's where we're going to start next time. Now, one or two of the, skip the homework about closures, because we haven't even mentioned closures yet, and those are those are sort of hard to. We'll do those the week after. Sorry, I have to type this because the person who asked the question. Yeah, we won't discuss the closures homework next time. We'll do it the week after because we haven't even got the closures, which is the last section today. But we have got into macros, and there are one or two macro problems, so do try to do those. And you might look at the additional slides. We'll start at slide 86 next time. As I say, this may look like we're going to fall behind before the end of the course, but in fact, the slides are a little unbalanced, and the first day has too many slides, and the rest of the days are more reasonable. So see you all next week. Thank you all for coming, and that is the end of the recording for today.
Okay, have a nice day.
Thank you, David.